at PUC Rio de Janeiro. After that, he got a master's in 78 also at PUC. And then he got another master's in 81 and a PhD in 83 at the International School for Advanced Studies in Trieste. And then he had a sequence of postdocs from 83 to 90 at ICTP and CISA in Università Trieste, all these three in Trieste, obviously. And then his last postdoc was at CBPF. And currently he's the coordenador científico do Grupo de Física Teórica José Leite Lopes on CBPF. And today, Professor Rafael will talk to us about the fundamental interactions and the third round of the Large Hadron Collider. So it's a pleasure to have you here. Thank you very much for accepting to talk to us, and the microphone is yours.
Okay, thank you so much to you, to Edson, to George, and to people at Federal de Uberlândia for the invitation. It's my first time, in contact with Uberlândia. I have just passed it by, but I never stopped to have a talk and to interact with people at the university in Uberlândia. I know some students who came to CBPF during our schools, our winter schools, but I've never been there. So it's a pleasure to be there, even though it's virtually. So my talk today, as George said, is on the fundamental interaction. It's mostly the third round of the LHC, because there is much still to see, and there is much still to fight, to keep, the standard model alive. So I just would like to remind here that this year we have the centenary of a very interesting paper by Compton, the same Compton of the Compton scattering. It's a paper published in 1921, so it's 100 years ago. In this paper, he already anticipates the ideas written in the ideas published by Uhlenbeck and Goldsmith in 1925 on the magnetism of the electron. So in this paper published in the Journal of the Franklin Institute, Arthur Compton gives his description and gives his modeling how the electron could be magnetic, and somehow he anticipates the idea of the spin of the electron. So I think it is interesting to celebrate this paper. So we are in a graduate program now with people doing master and PhD, and I think it's very good that we make connections with the past, because research in physics and research in general is a cumulative process. So we have to see that something which has been written perhaps 100 years ago, 125 years ago, it's still now having influence on what we are doing these days. So, so just to remind, now we have a problem, which is something flashing ready to the standard model. I'm sorry that my slides are written in Portuguese language, so MP is Portuguese, modelo padrão, standard model. So, I'm speaking about attomagnetism because atto is 10 to the power minus 11. So we are talking about the muon, which is a lepton, an elementary particle. So recently, now published on April 7 this year, 2021, there was a paper published by the Fermi National Laboratory in Chicago, where it's a Physical Review Letters paper, where they show that there is a clash between the experimental and the theoretical value of the magnetic anomaly for the muon. This is a very important piece of work which maybe is opening up new trends to understand physics beyond the standard model. I will come to that later on, mostly at the end of the talk. I just want to announce that we are talking about structures which are femto, which are at the femtoscale, at the attoscale, but on the top of that, we also, there is something that also I would like to remind, that is the Bright-Wheeler process. Brightwheeler process was studied in 1934 by Wright and Wheeler. And up to now, now we are talking about 7 years, still this process has not been yet directly detected. So I give here two interesting references on these works by Chinese people who are they are giving instructions how we could measure the Brightwheeler process by using these very high power lasers. The Brightwheeler process is a very simple process that we study in our undergraduate course. This is photon plus photon giving rise to a pair electron-positron. So it's materialization of two photons. So gamma plus gamma into E plus E minus. So this is a process which has not yet been directly detected. So now with the SULF, these Shanghai ultra laser facilities, which, I mean, they are dealing now with lasers of this sort of power of 10 pentawatts. So 10 to the power 16 watts. So this means that these lasers they are associated to very high electric and magnetic fields. And these high intensity fields may probe the quantum vacuum structure. And perhaps they give instructions how to detect E plus E minus from this gamma plus gamma process with the help of the laser, SULF laser. It's a 10 petawatt laser or frequency modulated laser field. So I give here these two references because I think they could be instructive in courses we are teaching. If we are teaching a course on QED, or even if we are teaching a course on spatial relativity or a course on advanced quantum mechanics, it's interesting to go through these papers because the students can see or can perhaps make even exercises on what is written in these papers here. So it's something that I would like to call attention to because it is related also to a process which has not yet been detected in the standard model. So another point which is important. Now we go to the other, let us say, to the other edge of the arrow. We were speaking up to now about the submicroscopic processes. So processes at the femtoscale, attoscale. Now we are going to the cosmological scale. Now we are talking about recent results on a magnetic universe. So what is the relation between the magnetic universe and the standard model? Which are the motivations to go through that? So let us just remind that 10 to the power minus 10 seconds, so this means that 1/10 of the nanosecond after the Big Bang, the universe underwent its electroweak phase transition. And so that is the moment where some magnetic field was generated in the universe. So what we call magnetogenesis. Now, so it's very important to have this in mind because we can understand this initial, this early universe process to see how the standard model may model or how this, where the standard model may fail to give, to reproduce situations and effects which were present in the early universe. So this is why I'm calling this, I bring these points to discussion. Also, let us remind that we go from the micro scale by considering the electroweak phase transition, which takes place at a scale of 10 to minus 3 femtometers. So this means that 10 to minus 18 meters. And we are talking about magnetic fields which spread in the galactic space. We are talking here about scales of 10 to 17 kilometers. So we have this very huge range of length scale. And we have to understand whether or not standard model works okay all over this big and huge range of length scale. Now, let me remind these two results, which are very important too, because here we are talking about magnetic monopoles. Magnetic monopoles, as we are going to see later on, they were predicted in a paper by Dirac in 1931, 90 years ago, but it has already been anticipated at the end of the 19th century. By Pierre Curie, around 1894, Pierre Curie was uh, pushing forward the idea that there could be some sort of atom of magnetism. Now, but okay, Dirac came to the question in 1931, and okay, all over these almost 100 years, magnetic monopoles have been searched for. But here we are seeing that we have already evidence for magnetic monopoles, but not the elementary magnetic monopoles as Dirac predicted. Here we are talking about collective states. So magnetic monopoles, which are collective states in spin-ices. So I give these two references because they are very important too. And my idea, my experience says that most of the students, when they come to CBPF, they think that it's forbidden to talk about magnetic monopoles. So I'm just saying that magnetic monopoles have already been detected, but which sort of magnetic monopoles? Composite magnetic monopoles, pseudoparticles in condensed matter physics detected in spin ice. So I give these two references, which I think they are very instructive to discuss the issue. Now, again, a very important discovery of last year, 2020. A fast radio burst associated to a galactic magnetar. So this is very important also to probe physics beyond the standard model, because we are talking about radio waves. So this means electromagnetic waves, which are propagating in a medium dominated by a very strong magnetic field. So okay, we can call the Faraday effect, which is the influence of a magnetic field on the propagation of the light. But here we are talking about a very huge magnetic field of around 10 to the power 16 Tesla. And so this means that perhaps we have to search for new extensions of the electroquick theory to understand how this phenomenon of these radio bursts can occur in these galactic magnetars. Also, another important discovery is that what the authors call the magnetic soul of the universe. This means that we have a very huge region of the universe, 10 to the power 20 kilometers, or 10 to the 7 light years, of a space completely filled in by magnetic fields. So I have a big region of the universe, or big regions of the universe, where there is a strong magnetization. And this could be very important to solve a question which is also beyond the standard model of particle physics and beyond the standard model of cosmology, which is the so-called Hubble tension. What is the Hubble tension? I have a slide here just to be more, let me jump here, slide. Opa. No, so just to give numbers, no, it's a baby before I have just jumped here. Sorry, I'm coming back here to, here. Just to make more clear to make clearer what is the Hubble tension. The Hubble tension is a discrepancy that we find in the measurement or in the calculation of the Hubble tension if we consider early universe data in comparison with the present day date of the universe. For example, the late universe, our present universe, we use supernova data and we get a Hubble constant, which is 73.3 kilometers per second megaparsec. If we go back to the early universe data as collected by Planck telescope, we get 67. So there is a clash here. And this discrepancy is nowadays in the range between 4 and 5.8 sigma. So this means this is the Hubble tension, this mismatch between the calculations of the same physical quantity by using early universe and late universe data. So it's a problem for the standard model of particle physics and for the standard model of cosmology. Let me come back here. And so what I mean, it means, it seems that these results here on the presence, of the very huge magnetized regions of the universe may give some hint to the solution of the Hubble tension. So this is a very important discovery made last year. I will give you the reference of this paper a little bit later, because I'm also saying that these are topics that we can take to the class to discuss with our students. Because my point is at the end of the talk, I should make a comment on that, is that sometimes our standard course is on electromagnetism, quantum mechanics, even statistical mechanics. They are not, let us say, very updated with the current research. So I think these are very interesting topics that could be present in a course on electromagnetic theory, even at the undergrad level. So these references are very welcome to enrich our courses. So we have that discovery, that we should celebrate, because perhaps it's going to solve a very drastic problem of the present day cosmology and of the standard model, this is the Hubble tension. Here, I give you a very good reference paper written by these three authors. I think they are from Catalonia, from Barcelona, tensions between early and late universe. So here in this paper, Nature Astronomy, they discuss in great detail the problem of the Hubble tension and the possible way outs to solve the Hubble tension. So it's a very good reference for students to, regardless of the research area, because it is physics, it's general culture that we have. This is a very big problem in physics. It involves electromagnetic theory, it involves relativity, it involves quantum field theory, it involves standard model. So this is why I think these are very good papers to enrich our lectures. So here, okay, magnetic fields, they are long, they have a very long steady state in the universe, contrary to the electric fields, which are very localized. And they soon vanish. Because electric charges tend to neutralize. So magnetic fields, they are much more standing. So this is why we focus much on the discussion and on the measurement of magnetic fields in the universe. So this is the paper I was talking about, this paper by Adamczyk and Pogosian, which tries to understand how the Hubble tension can be solved by using primordial magnetic fields. So these fields, which fill up these long extensions in the universe, they are maybe sort of fossils. They are maybe sort of remnants of cosmic magnetic fields. And that could be a first step to solve the Hubble tension. Sorry. Okay, just giving reference to students, maybe, because I understand that this is a talk directed, addressed to the graduate students at the Federal University of Uberlândia. That's interesting to read about this nice array here, this low frequency array, because this sort of detector, it measures magnetic fields or cosmic magnetic fields, astrophysical magnetic fields, by making use of the Faraday effect. So that's a very good lecture on electromagnetic theory. Now, if you come back to Faraday's effect, which was studied by Michael Faraday in 1845, when he understood that magnetic fields could have effects on the propagation of light, which was a very good inspiration for the work by Maxwell, some 20 years later in 1865. So it's a very good illustration of the Faraday effect by using some thing which is very, let us say, very present nowadays, which is measurements made by this LOFAR, which is a lab, which is an array localized in North Holland, in the Netherlands, no, but north part of Netherlands. Maybe I don't know if Netherlands has north and south because it's so small, but okay, anyhow, it's considered to be north of Holland. Okay, LOFAR, so keep in mind that. Also, this work here, 2021, so this is a phenomenon that has to be understood here, a very fast magnetic field amplification in distant galaxy clusters. So standard models of fundamental interactions and the standard model of cosmology, the lambda CDM. Very recent paper also by Juan Maldacena, published in JHAP, no Journal of High Energy Physics, that the study, the investigations, he start to comment, he presents some comments and some sort of investigations of the possible existence of magnetic black holes. So this is very important too, because this picks up a very precise point in the standard model, which is the how to modify, how to extend electroquick theory by introducing effects coming from quantum gravity. So that's a very nice, a very interesting mixing between quantum gravity and electromagnetic or electroquick theory. So I think we have been motivated. No, so these are the motivations to see what comes after, what comes beyond the standard model. Here, just would like to call attention to people, to the students, most of the students, that nature gives us some intrinsic electric and magnetic fields. If we combine the electron mass, which is the carrier of the electric current, the velocity of light, so this means that I'm talking about a relativistic effect, the fundamental charge, so I'm talking about electricity and magnetism, and H/, I'm talking about quantum mechanics. So by putting together all these fundamental constants with these specific powers here, I get something here which has the dimension of an electric field. And with this other combination, I get a magnetic field. So 10 to 18 volts per meter and 10 to 9 Tesla. So these are very, very huge electric and magnetic fields, which are able to probe the structure of the quantum vacuum. So this means that so this is something that nature gives us just for granted. We are not calculating fields produced by current distributions or current or charge distributions. We are just putting in a suitable combination fundamental constants of nature, and we get we get what we call the critical electric and magnetic fields, or critical Schwinger fields, which are the fields, the field strengths which are able to detect quantum effects of the vacuum, and they immediately modify, introduce nonlinear corrections to the Maxwell's equations. So, this is the time, the scale of time naturally associated to this process, 10 to minus 15 seconds. So in terms of frequency, this is 10 to 15 hertz. So this means that we are talking about something already at the edge of the ultraviolet. So here I collected, I think it's important to, if we want to go, if we want to confine ourselves to the magnetic sector of the standard model, I think it is important to understand a little bit how magnetogenesis has been studied all over these almost 70 years. So I give here, the references I consider the most important to understand the area. So we start in 1950 with this paper here about on the rays of magnetic fields in stars and in the interstellar space. This paper by Fred Hoyle, which is also an important paper published in the 11e Conseil de Physique de Solvay. Later on, we have papers by Zeldovich, a magnetic model of the universe. That's a very nice piece of work. Kip Thorne also studied the possible origin of the magnetism in the universe. After that, Brown, the generation of magnetic fields, and Harrison, Ted Harrison here, generation of galactic magnetic fields. This, I'm giving the historical reference because I'm going to send these slides to the organizers, maybe to share with the students. So if you want to make a sort of a recollection of the timeline, I think it is important to understand how the field evolved and to be, aware of the scientific process. Here another paper by Ted Harrison, how magnetic fields were generated in the radiation era before there was the decoupling between radiation and the matter. So it's important to understand what are the mechanisms behind the generation of the magnetic fields in the radiation era. Here, another Ted Harrison, magnetic fields in the early universe. And more recently, this very good paper by Dario Grasso and Rubinstein, these two researchers from the Padova University in Italy. They have this very beautiful physics report paper, explaining, giving all the historical background and the present day understanding of how magnetic fields were generated in the early universe and how they evolved up to the mean value we have today of 10 to minus 8 Gauss in a scale of 10 kiloparsec. So it's important also because these are things that had to be discussed by the standard model. Here another paper, a very recent paper, 3 years ago, to be or not to be, primordial magnetic fields from viral anomaly. So here, a very good way of mixing quantum field theory, viral anomaly, dilatation anomaly, with the generation of magnetic fields. So this is something which is very important in connection with the standard model too. A very nice link between quantum field theory, which is the discussion of the anomaly, the viral anomaly, and viral anomaly is connected to the renormalization process, to the breaking of scaling invariance, and the generation of magnetic fields. Now, if someone wants really to understand and to be in the heart of the discussion of the importance of magnetic fields in cosmological process, I have this line of research initiated by Tanmay Vachaspati. He works in the Arizona State University, and Vachaspati initiated in 1991 a very regular, a very systematic line of papers discussing magnetogenesis. So it's very important because he makes a very good connection between standard model and cosmology. Now, another question related to magnetism, but not at the cosmological, astrophysical scale. Now we are talking about the femtoscale, submicroscopic scale. The magnetic monopoles predicted by Dirac in the same paper in which he predicts the existence of antimatter, published in 1931, and this paper gave Dirac the Nobel Prize in 1933. So this is the discussion of, the work Dirac really predicts on the basis of quantum mechanics and the relativity, the existence of magnetic monopoles. Okay, let us recall that years ago, some sort of 37 years before, Pierre Curie had proposed that magnetic monopoles should exist. I think this is very touching piece of information, because at this time, not even the electron had been discovered. At this time, there were no elementary particles. The electron has been discovered only 3 years later, 1897. So Pierre Curie was already anticipating the possible existence of what he called atoms of magnetism, so the magnetic poles. Poincaré soon started to study the mathematics connected to the solution of magnetic monopoles in presence of electromagnetic fields. Thomson had a nice set of lectures. I'll talk later on, in the next slide. And Dirac, 1931, Igor Tamm, 1931, also discussed after the work by Dirac. Igor Tamm initiated a very intensive research on the interaction between electrons and monopoles. Here, Henri Poincaré didn't do that because at that time the electron had not yet been discovered. And this paper by Qcd here is the first paper, where the author tries to detect a possible magnetic, a possible Dirac magnetic, but which was not possible because up to now, up to these days, Dirac monopoles have not been discovered, only composite monopoles. This is a very nice. This is the paper by Thomson in 1904. It's electricity and matter. A set of lectures he gave at Yale, and he shows how angular momentum could appear naturally from the interaction between charges and monopoles. It's a very historical paper too. Now, if we are going, we are in the heart of the standard model. So we have, the heart of the standard model are the non-abelian gauge theories, Yang-Mills theories. And all these Yang-Mills theories, they have a series of phases, like electromagnetism. We know more, from our undergrad and graduate courses, we know more the Colombian phase, which has a potential which is 1 over the distance. But we can have other phases of electromagnetic theory, a logarithmic phase, a logarithmic magnetic phase, the Higgs phase, and the confining phase. So we have a very rich spectrum of phases of a gauge theory. And standard model is nothing but a combination of gauge theories, SU3 for color, SU2 for the weak iso spin, and U1 for the weak iso charge. So we have here the diagram of phases, the possible phases. And here we have to see, from these phases here, we have to understand where we have to go beyond the standard model, why we should go beyond the standard model, and some of these phases may show that to us. This is what I'm willing to say. Now, this paper by Toft here, published in 1975, where he discussed the unification of the standard model. Basically, this is a paper on the standard model, and Toft in this paper discusses the possible phases of the standard model. Also, this paper here of Mandelstam by Stanley Mandelstam is very important too in this discussion. Now, here, let us recall how this standard model effects are present in the phase transitions of the early universe. So 10 to minus 38 seconds after the Big Bang, we have the first big phase transition. We go from the grand unified phase into the standard model phase. So at this stage here, we are talking about a temperature of 10 to 30 Kelvin and energy scale 10 to 16 GeV. So at this stage here, we have, from the Planck scale 10 to 19 GeV to the 10 to 16 GeV, we have quantum gravity and grand unification, both separately. So at 10 to 16 GeV, the grand unification breaks down into the standard model. And so we start physics, from our physics, of the standard model from 10 to 16 GeV. 10 to minus 10 seconds after the Big Bang, we have the electroquick phase transition. So at this point, it's what we call the Fiat lux. At this point, we have the appearance of electromagnetic field, as I'm going to show here. Let me take here. So the Fiat lux takes place here, at 10 to minus 10 seconds after the Big Bang, when we have for the first time, the appearance of the electric charge. So we understand that we call electric charge today comes from this quantum number associated to the weak isospin and the weak isocharge. So have here this combination, this particular combination gives to us what is the electromagnetic charge, electric charge, present in this phase of the universe. Here we are today. We have SU3 color, Qcd, and we have U1 electromagnetic, we have QED. So electroquick theory was unified up to here, up to this scale of 10, as the energy scale I showed here, 250 GeV. So at this stage here, we break down, we split the electromagnetic and the weak nuclear interactions. And the photon appears here. Here we have the appearance of the photon, which is a particular combination between the let us say, the carrier, the mediating field associated to this U1 symmetry, and the mediating field associated to this SU2 symmetry. And this angle here, this so-called Weinberg angle, we know today that sine square of theta w is around 0.23. So this is one of the coupling constants of the electroquick theory. And we know its value today measured at a scale of 90 GeV. Okay. Afterwards, we have the last phase transition, the Qcd phase transition, which is taking place 10 to minus 5 seconds after the Big Bang. So much later than the electroquick phase transition. So at this scale here, quarks get confined. So now, from now on, quarks and gluons are confined into the hadrons. What we say that the LHC is doing in its LHC collaboration is to reproduce this situation here in a collider. No, it's to reproduce let us say, the phase where quarks and gluons were unconfined. Okay. So this is just, I mean, a sort of very short, just that. Here's a sort of very short picture with these three-phase transitions: the grand unification breakdown, the standard model breakdown, and here the latest phase transition we have, which is the confining phase transition. Here, just a very simple presentation of the set of Young-Mills theories, showing that what is in black is Maxwell's equations. What is in green is the corrections due to the Young-Mills extensions. Also, these are the nonlinear extensions of the Maxwell's equations by introducing this idea of the Young-Mills fields, which is the idea which is behind the standard model. So when we talk here about the SU3, SU5, which is the grand unification, SU3 color, SU2 weak isospin, and U1 weak hypercharge, we are talking about Young-Mills field. So we are talking about this set of equations here. And interesting is that the Gauss equation, the Gauss law for magnetic field in the Young-Mills, at the Young-Mills level, it has something which has non-zero divergence. So this is the place where we can have the origin of the magnetic monopoles. It's exactly here in this nonlinear piece here that magnetic monopoles may arise, may come into Young-Mills theory. So I'm talking about that because this will be a very important point to be tested now in the LHC in the experiment called Moedal. So here I give them just some references about the magnetic monopoles, how magnetic monopoles appear in different scenarios. So we have the presence of magnetic monopoles in grand unified theories. So these magnetic monopoles were present at the early universe. So if we take them into account, we have a chance to start understanding the Hubble tension. We have magnetic monopoles also in Kaluza-Klein theories when we talk about higher dimensions. We have magnetic monopoles also present in superstring theories. Magnetic monopoles are also present in theories of quantum gravity and cosmology. And magnetic monopoles are also present in the electroquick Salam-Glash-Weinberg theory. And this mechanism, this so-called dual mechanism by Schwinger, will be the way we try to understand, and we try to understand the presence of these monopoles in electroquick theory and how monopoles may eventually be detected in the third round of the LHC through the Moedal collaboration. Here, so I have made a sort of timeline of the appearance of monopoles in grand unified theories. Here, monopoles, again, in grand unified theories, monopoles in higher dimensions, how we can understand magnetic monopoles coming from higher dimensions, Kaluza-Klein theories, how monopoles are understood in connection with superstring theory. So superstring people also deal with magnetic monopole as a possible solution of their field equations, magnetic monopoles in quantum gravity and in cosmology. So these are two papers. This first paper by Abrayanti, it discusses how magnetic monopoles may come in quantum gravity. And here this paper by Szabo, how magnetic monopoles are present also in cosmology and quantum gravity. Quick monopoles, electroquick monopoles, which are in the heart of the collaboration or of the Moedal collaboration. So these are very important. This paper by Cho and Mason became a classical paper now. It was published in 1997, so 24 years ago, and this paper now is extremely up to date. And people are really discussing these ideas. Here also monopoles, instantons, and confinement. This work is very important. It was published in 2000, and it's an archive. It was never published in a journal, but it relates the discussions between monopoles, instantons, which could be sort of the quantum vacuum of the nuclear forces, and confinement. So this is some, let me tell you here. So this is something which is not yet completely understood by the standard model. So this is, let us say, an open problem in the realm of the standard model. So these papers here, production of magnetic monopoles in presence of magnetic fields. So we have here a theoretical ratio. We can calculate this ratio for production of monopoles in presence of huge external magnetic fields. So it's something which grows up with the second power of the external magnetic field. So this is exactly, this expression here is, let us say, in the focus of the Moedal collaboration for the next running of the LHC. So, these are, just giving more reference. This I would like to point out the presence of condensates of monopoles in superconductors. So this paper here, published this year, is very interesting paper which shows how magnetic monopoles in this. I'm talking about magnetic monopoles in condensed matter fields, matter physics, how they can condensate inside superconductors. So there is a connection also between monopoles and the dark matter. So dark matter is one of the focus, it's very present in the agenda of LHC. One of the collaborations which is going to study dark matter is just LHCF, that collaboration LHC forward. Here monopoles also in connection with supersymmetry, which is very important for the third running of the LHC. And this is a very recent paper by Mavromatos and Mitsu, where he makes it's a very good paper because it makes a very extensive revision and a very extensive reassessment of the measurements of the trials to search for monopoles in colliders and in the cosmos. So it's a very good paper if you want wishes to have a general idea of how magnetic monopole physics is seen nowadays, today. Here, another problem which comes this year. No, the problem of the, as I told at the beginning, no, the magnetism, no, the intrinsic magnetism of the muon. Okay, let I say the magnetic dipole moment of the muon. This is a big problem this year. It was published, as I told at the beginning, this year in April 7, 2021. I'm going to come back to these slides later. So just to show something here, that is the paper I'm talking about. So this paper here, published now in April, shows a mismatch, a clash between the experimental and the theoretical value calculated up to the 5th order, now in perturbation theory, in the standard model. And still there is this mismatch. So this means that maybe there is room for some good new physics in this problem. So just for those who don't know how we define the magnetic anomaly, we define like that. We have the magnetic moment of every particle. No, it's what we call the Bohr magneton for each particle. So it has a gyromagnetic ratio. Here the Bohr magneton, and here the spin. So quantum mechanics, together with spatial relativity, gives that every particle, each and every particle, which does not have, which has a spin, no, which has a non-trivial spin, must have gyromagnetic ratio exactly equals to 2. This is the result coming from relativistic quantum mechanics. But experiments show that for the electron, for the muon, for the tau, G is not 2. It's 2 plus something. So where does this something come from? It comes from the idea that quantum fields fluctuate. In quantum mechanics, we are talking about particles, localized particles. Okay, particles localized within the Compton wavelength. But quantum field theory, somehow it forgets the idea of particle, and it replaces particles for quantum fields which fluctuate. And these fields, they can probe many more effects that the particle cannot probe. So this is why field fluctuations and the idea of quantum field theory is very important to replace quantum mechanics in the understanding of the magnetic anomaly. The magnetic anomaly is defined like that. The gyromagnetic ratio is 2, coming from relativistic quantum mechanics. But quantum field theory adds some small portion here, some small quantity, which we call field fluctuations. And we parameterize these field fluctuations by introducing a concept we call a magnetic anomaly, which is defined like that. From this equation, we get that a magnetic anomaly is G minus 2 over 2. So the deviations from the value 2 divided by the value 2. So it's a sort of percentual variation, variation of the gyromagnetic ratio. So this is something that we calculate in quantum field theory, and we calculate to very higher orders in perturbation theory. And so this has been done. During 50 years, people have used this expression, which is the expression quantum field theory gives to the electromagnetic current. And by using this sort of Feynman diagrams, calculate this process, up to higher orders in perturbation theory to get the magnetic anomaly. And magnetic anomaly is proportional to the square of the mass of the particle. This is why the magnetic anomaly of the muon is much stronger than the magnetic anomaly for the electron, because muon has 200 times more mass than the electron. So this means that it will be a factor of 40,000. So the muon anomaly is 40,000 times more intense, stronger than the anomaly of the electron. So this is why people focus. This is a very good laboratory for physics beyond the standard model, is the magnetism of the muon. So, okay, this I just repeating here what I already said. And so this is the paper published this year, which shows this clash in the calculation of the anomaly. So let me just go to this slide here to show that the anomaly measured experimentally goes up to the 8th, 10th. Okay, so experimental value, theoretical value. They agree up to this digit here. From now on, we have a difference. This difference is this one here. So there is this match. So this match, this clash between the experimental and the standard model value. So this piece of work here, this piece of difference here is almost 4 sigma, 4.2 sigma, and people are improving that to arrive at a 5 sigma, showing that there is indeed a sort of failure of the standard model. So new physics might come in here. So people now are very focused on the magnetic moment of the muon. This is the reason LHC is going beyond that. Here also we have, it's very small, I don't know if people can read well, but these are the most important laser physics laboratory devoted to study magnetic properties of the quantum vacuum, how the quantum vacuum is nonlinear by using lasers of these categories here. So this XL is a laser at the exawatt scale, so 10 to 18 watt. It will produce very, very huge magnetic fields, which maybe will break the structure of the vacuum. So we can get currents, electron and positronic currents out of the vacuum by submitting vacuum to these lasers, to this power of this laser here. SELF is already working in Shanghai. CEL will start working next year, also coming to sort of 10 to 18 watts, and XLs may be to 150 exawatts. So this means almost 10 to 20 watts. So it will be really very, very strong lasers. So this opens up the possibility to study 17 nonlinear extensions of electromagnetism, of electroquick theory. So here I have collected sort of 53 extensions of the electromagnetic theory, 53 extensions, out of Maxwell, because we have here to contemplate new physics. Physics coming from effects coming from quantum gravity on the electromagnetic theory, effects coming from Higgs field, effects coming from quarks, effects coming from higher dimensions. So there are many effects going and coming and modifying Maxwell's equations. And among the nonlinear extensions, I classify 17 very interesting, which should be really understood by the standard model. Now, standard model has, so I'm about to finish, okay? So standard model has many limitations. So we have 19 physical parameters. And in the Higgs sector, we have 15 parameters. Let me show here. So it's not a good theory. It's a very, let us say, a very primary model. We have the gauge coupling constants. We have 2 parameters in the Higgs potential. We have the Higgs couplings to the leptons. We have the Higgs couplings to the 6 quarks. We have the mixing angles between the families of U, S, and B quarks. And we have the theta parameter, the theta vacuum parameter of Qcd. So we have a theory which has 19 parameters. And among these 19 parameters, 15 parameters are really in the Higgs sector. So this means that we have much to understand why there are so many parameters associated to the Higgs sector of the standard model. So this is a problem for the standard model, which should be understood by contemplating maybe a more fundamental theory beyond the standard model, of which the standard model is an effective theory. We have the problem of the gauge hierarchy. We have the problem to understand the origin of the mass. It's the only massive parameter of the standard model is the Higgs mass. So the Higgs mass is not calculable as the other masses are. The Higgs mass is an input. So we started the standard model by already plugging in the Higgs mass. So this is a very bad aspect. It's something, a drawback of the model. So this has to be understood, maybe, which is the new physics from which the Higgs mass comes from. Here we have the very huge difference between the Yukawa coupling constants of the Higgs to the quarks and leptons. We have a problem which is not yet clarified of the CP violation in the strong sector, the theta vacuum problem of Qcd. In the standard model, neutrinos are massless, so we don't contemplate the neutrino oscillation. So the so-called, this very famous PMNS matrix, no, Pontecorvo, Mach, Nakakawa, and Sakatamo parameters, which may give ideas, no, we may quantify how these neutrinos oscillate from one family to the other. There are three angles and one phase here. We don't talk about dark energy. We don't talk about dark matter in the standard model. Gravitational interactions are completely outside. We have the problem of the Higgs. Is the Higgs really an elementary particle? We don't know yet. We have problems. I mean, we have maybe indications that this B bar system, which I mean, this experiment called Bay Bar, it's carried out at SLAC. It is studying that maybe there is an excess of decay channels not predicted by the standard model, which could be maybe a way out to understand how supersymmetry could improve this difficulty of the standard model. We have the problem of the limit on the electric dipole moment of the electron. Standard model gives a value which is much, much smaller, orders of magnitude smaller than the experimental bound we have nowadays. And the asymmetry between matter and the antimatter, standard model does not explain baryogenesis, and why standard model has fermionic matter, but no scalar matter. Why is scalar matter forbidden in the standard model? The only scalar which is present in the standard model is the Higgs, but Higgs is not a matter field. Higgs is part of the gauge sector. So this is something, maybe a more philosophical questions, but which a fundamental theory should explain, should give to us, describe to us. So before many problems. The standard model has at least 13 problems that new physics might provide. Now, let me recall that the tetraquarks and pentaquarks were measured also at LHCb. And now LHC in the third round is going to go deeper in the search for penta and the tetraquarks, no? Because the standard model gives only hadrons, baryons, 3 quarks, and the mesons, quark and antiquark. No tetraquark, no pentaquark. So this is something which LHC already detected, 2016, 2020, and so we have to see how we could understand this on the basis of some new physics. The 8 experiments now of the LHC. Now this next run, we have the phaser, which is a new collaboration. We have LHC, which is it's very important because it has very relativistic heavy ion collisions. And so this gives rise to very strong magnetic fields. And with these very strong magnetic fields, we could study for the first time after 85 years, the light-by-light scattering between 2 photons, which have been studied in 1935, but never detected. It was detected in 2017. So LHC is going to get more precision in this measurement of the photon-photon scattering. Atlas, no supersymmetric particles, not yet detected, possible extra dimensions, anomalous coupling in the electric sector, especially the neutral anomalous coupling, and dark matter. CMS, Atlas and CMS make the same measurements. One try to confirm what the other discovers. LHCb, very important also to open up new channels of supersymmetry. LHCf, they mimic cosmic rays in laboratory. The toton is a deeper comprehension, a deeper understanding of the structure of the proton. There are many problems that we don't yet understand in connection with the structure of protons in terms of quarks and gluons. Moedal, detection of monopoles, dions, and massive particles which are metastable, let us say, pseudo-stable, metastable. And the phaser, this new collaboration is the forward search experiment, which is going to detect ALPS, axions and axion-like particles, dark photons, and very high energy neutrinos, possibly also the sterile neutrinos. So these are the new collaborations of the LHC. Here, future lepton colliders, ILC, International Lepton Collider, the CLIC, Compact Linear International Collider, FCC, and muon collider. Muon colliders are very interesting because they have very, very low loss of energy by synchrotron effect. So it's, envisaging, it's in the horizon of experimentalists to construct in the future muon colliders, maybe 2050, because these muon colliders would really improve a lot our precision tests and the discovery of new physics beyond the standard model. So just to finish up, I have some considerations, saying that electromagnetism is an old theory in physics. It started in the 18th century with the works of Benjamin Franklin, Charles Coulomb, Alessandro Volta. But electromagnetism is always renewed. Every time we have some new discovery in physics, this new discovery can be connected to electromagnetism. Electromagnetism is sort of a ubiquitous physics in the nature. So we should really improve much our knowledge of electromagnetic theory. Electromagnetic theory is a sort of Peter Pan. It's always a child. It's always a theory which is always in the first moments. We are always restarting. We are always renewing electromagnetism. So if we consider femtophysics, if we consider exophysics, cosmological physics, electromagnetism is always involved. So I believe that it is time to start improving our courses on electromagnetic theory. Now, we are very much attached to the Jackson book, which is an old book. So why not study electromagnetism on the basis of this new phenomena that we are measuring and we are trying even to detect? So I like to quote here this French philosopher, Maurice Merleau-Ponty. He has a very beautiful course delivered at the Collège de France called The Nature. And here he says that it is inner criticism of physics which yields us to be conscious of the perceived world. And he says that the world we see is not at all something which is immediate. So there is much behind the world we perceive with our senses. So I think this is important in physics, to see that beyond every phenomenon which might be simple, there are lots of new ideas that are very abstract, and mathematics can help, and new experiments are also important. So I think this is a very important quote by Merleau-Ponty. in this book, The Nature, he has a very nice section, in the chapter 1 about the philosophical signification, philosophical meaning of quantum mechanics. It's something that the students should read. It's very nice. I mean, it makes. I'm not saying that what he says is true, but he leads us to think a lot. He makes, many sorts of arguments that we have to, to discuss, and we never end the discussions because they are very deep points that he makes about physics, that he considers about physics. Sorry, there is also someone that I would like to quote to students, Paul Feyerabend. Paul Feyerabend, he was an Austrian physicist, and he was a sort of anarchist as long as the scientific method is concerned. But he has some quote here that I think is very interesting to say that in science, sometimes we have to break standards. We cannot be well-behaved all the time. We have to break standards. We have to make some anarchy in order to find new phenomena. I think Paul Feyerabend is someone that we should sometimes read to try to take to our courses to see how he's a very clever guy. What he writes is very interesting and makes a lot to know. He brings a lot of reflections for us to think about. So I'm quoting because maybe, it's literature. His literature is not very present in the courses, and so I like to quote. In 2 years' time, there will be his centenary. Here, Al-Haytham also says the same thing 1,000 years ago, 11th century, 1021. He writes a book, Doubts on Ptolemy. And he says that we have always to learn things, knowledge that has already been produced by always criticizing. So he puts them in, this is 1,000 years ago. He says that criticism is the main leading part of doing science. It's the main leading process of doing science. Criticize those who wrote the things we are nowadays studying. Criticize does not mean to deny. Criticize means to think about and to really make a scrutiny on what we are learning. So I think this is something which should be emphasized in our courses. So here I leave my contacts at CBPF. And we have this site here, Professor Global, where we have many courses for undergrad students, for graduate students, open, and we have many sections of talks, discussions that are available for students. So everything here is given for free. So it's www.professorglobal.com.br. So I would like to thank Werneck. I would like to thank George for this nice invitation and this nice opportunity to interact with people in the Mineiro Triangle, people at the Uberlândia and Uberaba maybe. So thank you so much for the invitation. And here I am, if we have time for some discussion.
Thank you very much, Professor Hilaire, for the very nice talk, very touching, very we have open for questions. We are open for questions. I am sure that Edson has a question to ask. He always does.
Okay, here I am.
Well, thank you very much for your nice talk. It's, as I said at the beginning, it's very nice to see you again.
Okay, thank you so much.
Even though we are still in virtual mode.
Yes.
My question, I have plenty of questions, and I'm afraid they are kindergarten questions for you. I will not make all of them because George is always, afraid I take all the time. But I'll try to be short. Our program is essentially condensed matter, so many stuff you you told us is kind of new for me. I have to say. So when you at the beginning, so let me put my first question in this point. So you start talk about magnetic, how to say, magnetic universe, something like that.
Magnetic domains in the universe. Okay.
Right. Okay. So so that's better. Explain a little bit better for me, because at some point you prefer to talk a magnetic realm, I'd say, in detriment of electric. So could you hope to see some symmetry between these two fields?
Yes.
Right.
Yes. Okay. You see, the problem is that the universe, let us say, the big structures of the universe in general, they are neutral. Now, stars are neutral, but they are magnetized. I mean, like an important electric field. Okay, we have a dipole, an electric field produced by the electric dipole, but most of the magnetic and most of the electromagnetism of the Earth comes from the magnetic part. So we have a magnetic field. The stars have magnetic fields. Rotating stars like pulsars, like neutron stars, they have a very strong magnetic fields, but they are in general neutral objects. And also the tendency of the charges, the free charges of the universe, they tend to neutralize, charge, matter and the antimatter. So most of the universe is neutral. So this is why in the universe, which is, let us say, remnant from the early universe, are the magnetic fields. So magnetic fields are, let us say, a very good inheritance that we have from the early universe. That's my question. That's my point.
So this breaks somehow the symmetry between electron and magnetic fields.
Yes.
Okay. Or break the degeneracy, I'd say. I think it's this way is better. George, can I make another one?
Yeah, just there is a question here that was written. You can read in the chat if.
Okay. Renato Doria.
Yeah, Renato Doria.
The Higgs has been directly detected at tree level or only indirectly, as in 2012, by means of the decay into photons. So let me answer to Renato Doria. We say that the Higgs was not directly detected. We detected the Higgs through its decays. So we had the decays of Higgs into two photons and the decays of Higgs into Z0 and Z0 star. So the Higgs was not directly detected at tree level. It was produced as a resonance. This resonance has decayed into two channels. And so photon-photon, special photon-photon channel, and Z0 star. So my final answer is that it was not directly detected at tree level.
Edson, Yeah, Edson, you had one more question.
I had many more, but my second question is in connection when you talk about monopole.
Yeah.
To say that, let me call them maybe not the best, but the monopole, the traditional monopole.
Yes.
And the monopole we observe in condensed matter physics. So are they? So they are kind of similar at the first side, but it may not be when you go to the second phase. Where actually these comparisons break down.
Okay. So let us say the true monopoles, let us say the Dirac monopoles, they are considered to be elementary particles. So they are considered to be structureless particles, like the electron is up to now. Up to now, we have not seen any internal structure for the electron. So Dirac's monopole is something which is an elementary particle. So it has not yet been detected. If we go to not to grand unification, let us say if we go to Young-Mills theories, so grand unification, electroquickie, or other, Tufte-Polyakov. So we have, let us say, the so-called grand unified magnetic monopoles. Magnetic monopoles which appear as topological solutions of the Young-Mills equations. So these monopoles are complex structures. They are complex stuffs. So they are made of Higgs fields. So if we consider the structure of a magnetic monopole in grand unification theory, also let us say these magnetic monopoles which are going to be searched for in the LHC next round. So these are complex composite monopoles, and they have a very, let us say, complicated, complex structure in terms of other fundamental fields. Now, in condensed matter fields, in the spin ices, these monopoles which appear, they are monopoles made of spin domains. So let us say, it's a sort of array of spins, which at the end of the day, they are composed and they form some sort of open lines magnetic fields. So these are three different, let us say, categories of monopoles. Now, the monopoles in spin ice, so they are pseudoparticles of condensed matter physics formed in these artificial spin ices. So we have the Dirac monopole, which is an elementary particle, as the electron is, never detected. And we have the Young-Mills or grand unified monopoles, which are sort of a complex structure, a complex particle made of Higgs components of the Higgs fields. So this is the monopole which is going to be searched for in the LHC.
Okay, so theoretically speaking, so the one that has structure,
yeah,
could describe then in terms of a field for that describe the individual components of these objects, right? So
yes,
they could be called quasi-particles.
Yes,
yes, right.
That's right. Right.
Okay, thank you very much.
I'm seeing here another question made.
There is another question from Renato. Yeah.
Yes, the Higgs is unique, or there must exist a family of Higgses. Speak about the universality of the Higgs. So, in the standard model, the Higgs is unique. But if we want to introduce neutrino masses, so we have to bring about another Higgs family. The Higgs present in the standard model, as pointed out by the very famous paper by Weinberg in 1967, the paper which yielded him to the Nobel Prize with Salam and the Glashow, the paper by Weinberg is very precise. He says that there is a doublet of Higgs fields, and this doublet must have these attributions, these quantum numbers under SU2 and 1 symmetries. So this was the great contribution of Weinberg to the Salam-Glashow-Weinberg model. Now, if we wanted to introduce neutrino masses, and neutrino masses are not allowed, they are not present in the standard model, we have to introduce a triplet of Higgses. So Higgs is not unique as long as we want to introduce neutrino masses. Now, if we go to supersymmetry and we consider a sort of reassessment of the standard model in a supersymmetric space-time, in a supersymmetric framework, we must have 5 Higgses, 3 Higgses, 3 neutral Higgses, and 2 charged Higgses. So Higgs is unique only in the standard model without massive neutrinos. By introducing neutrino masses, I have to bring at least a triplet of Higgses. Now, if we go to the supersymmetric extension of the standard model, the so-called MSSM, minimally supersymmetric standard model, we must have 5 Higgs. So Higgs is not universal. Higgs is not unique. sometimes we can put as many Higgses as our needs ask us to do. So I hope I have answered to Renato Doria.
I have a question. It relates to Edson's question about the spin ice. We who are doing topological matter, we study Dirac's equation, and we learn that graphene has a low effective model, has a Dirac equation, so you expect to see Dirac electrons, so on and so forth. In the case of the magnetic monopole and in the spin ice, do we have the same situation where the effective model for the spin ice is exactly the same as the equations that Dirac was studying?
No, no, it is not.
No.
It is not like, I think, let us say the dispersion relation is not linear.
Okay.
So you cannot have, I mean, a sort of a parallel to Dirac's equation by replacing the velocity of light by the Fermi velocity. It's
okay.
not quite the same, okay?
Okay, so there is no, the parallel doesn't work so well as in the case of the graphene.
No,
okay.
no, yes,
okay.
That's true, George.
Okay.
That's true.
Okay, okay. I have another question. By chance, just yesterday I was reading in the BBC page, they announced that the collaboration, I won't remember the name of the collaboration at the Fermi lab that didn't find the sterile neutrino. They say that they didn't find any hints of this sterile neutrino, but I overheard you saying that one of the LHC experiments is going to look for this sterile neutrino, right?
Yes, it is the phaser. Let me put here, so just for you to make clear your idea, no, just
okay.
to keep in mind, it is this collaboration called the phaser, because I mean, I'm coming to that.
But do you know what experiment I am talking about? That I don't remember the name is.
Yeah, there is this collaboration in the Fermi lab. I mean, the neutrino collaboration. I forgot the name too, but it is very. I mean, it's one of the most important collaborations for neutrinos. It's the phaser. No, phaser is going to measure some of these axon-like parts and also very high energy neutrinos. And I didn't quote here, but what I know from the CERN is that the phaser also is going to search for sterile neutrinos. Because, you see, the sterile neutrinos, they only interact gravitationally. So they are very similar to these dark photons.
Okay.
So the same, let us say, the same technology that you can use to detect dark photons and some of these ALPS, axon-like particles, you can apply to study sterile neutrinos because they don't interact with any particle of the standard model. They only have gravitational interaction, and so they are dark matter. So where we search for dark matter, you can also search for sterile neutrinos. I asked myself, I don't know, if in the atlas, since there is a focus on dark matter, if this dark matter to be searched for at the atlas is also including sterile neutrinos. This I don't know, but I know that the phaser is going to search for sterile neutrinos. That's I know.
Okay. So I understood from what I read yesterday,
yes.
Partially understood, is that the non-existence of the sterile neutrino would agree with the standard model, right?
Yes.
Okay.
This would not deny the standard model. This would be a sort of confirmation because the standard model does not predict the existence of sterile neutrinos.
Okay. So if we do we have any more questions, comments, or Edson? I know that you have a list. So
just write me up. Get in touch and we try to discuss. No problem.
Yeah, we're gonna. I didn't notice if Edson mentioned that we are recording your talk. we're gonna
Yeah.
we're gonna post the talk in our YouTube channel, and then I'm gonna ask for the slides for you to send me by email. Yeah, and then we post everything together, and I am sure that almost the same number of students that I would say that exactly the same number of students we had at the beginning, they are still here. So they are excited about. Yeah, they are excited. Yeah, this subject always brings new ideas and is interesting.
Yes, and I mean, since the students are present, you see, George, you are a teacher, you are a professor, a lecturer. Edson is a lecturer. Renato Doria, I know him very well. We are good friends. Renato Doria is also a professor. So, I mean, we know that we have somehow to touch our programs. At least this more considered a basic course like electromagnetic theory, quantum mechanics. I think we should have an update of these courses. I think the electromagnetic course here in Brazil, we are always talking about the same thing. It's the same Maxwell equations in the undergrad, in the master. So, okay, Maxwell equations are fundamental. But there are much more intelligent life after, beyond Maxwell's equation. And so all I talked here could be brought into a classroom. We could bring these papers to discuss with our students, to discuss magnetogenesis. So let us study other situations, where we can learn electromagnetic theory without necessarily going to a coaxial, to study antennas, to study all this stuff. Let us consider our antennas as being our neutron stars, as being our gamma ray bursts. So I mean, I think we should now start giving more motivation to our basic courses and understanding that our students, they are clever enough and they are much more motivated and they acquire self-esteem if they feel that, okay, I'm doing basic electromagnetic theory, but in another scenario, I am considering things that are being understudied now that maybe will be a Nobel Prize, that will be the subject for a Nobel Prize winner in in some days, in some years, like these big lasers, these very high powerful lasers that we could do a lot of physics to study propagation of electromagnetic waves in the presence of these very strong, very powerful lasers. So, I mean, this is what I somehow would like also to convey this sort of message from my talk. Also thinking about the teaching of physics, for example. Just that. I'm very grateful for your invitation, for your organization. I mean, you people are, Swiss organizers, very good.
Thank you very much. We try. Let me ask you the following. You mentioned your webpage at the end? Do you have material there that we could borrow and that would enrich?
Sure.
Okay.
Renato Doria is here. Renato Doria is the person who organized this Professor Global. So if we enter Professor Global, you register there, you don't pay anything, you just register, and we find many courses, even videos, courses we teach at CBPF, they are there. Because you see, George, what we understand is that you people, you are working in universities, so you have a lot of duties. You have courses, undergrad course, graduate course, you have a lot of bureaucratic charge also. So we at CBPF, we have a much more relaxed life. We don't have an undergrad course. We just teach to graduate students. So, our charge of courses is very little. So we try to produce many courses and to put these courses, to make these courses available for students from other places of Brazil. Maybe, I don't know, if at Uberlândia there is no one who can teach a detailed course on the standard model. So we have a course on the standard model. We have courses on, let us say, nonlinear electromagnetic theories. We have courses on Dirac's equations. We have courses on group theory, just to help. You see, and we are also very glad if you people place your courses in Professor Global also. Professor Global is something that we want to make a sort of library of courses taught around Brazil, not necessarily our courses, you see. So, let us see that, let us share this the web page.
we're sure gonna check on it. We're sure gonna check on it.
Okay.
Yeah.
Here we are. And Renato Dori is the person who organizes that.
Very nice.
Thank you so much.
Just a final comment, because I was very glad that you mentioned Paul Feyerabend at the end.
Really?
I teach a course here where I talk about Popper, Thomas Kuhn, and Paul Feyerabend. I don't talk much about Paul Feyerabend because the course is not about epistemology. It's introduction to research. But I was very glad that you talked about him.
So we are organizing a meeting in 2025 on the centenary of Paul Feyerabend, and we are going to invite you then.
Okay, thank you so much.
It's a deal.
Okay, 2025 you said.
Yes, in 3 to 4 years time.
I will have time to prepare something, a little something. Okay.
Very good. Okay, people.
Okay,
Bye-bye.
so thank you very much for the nice talk, and thank you for accepting the invitation.
Okay, my heartful thank you to you. Bye-bye.